So I'm going to talk about several things around Kafka. Who here, besides the Brandwatch people, use Kafka? Who knows what it is already? Okay, this is going to be tough. All right. So I'm going to talk about what Kafka is and what it does. Kafka comes with its own little ecosystem of terms, so we're going to go through a whole bunch of those, and that will explain all the different parts of what Kafka is. We're then going to talk about the different APIs that you can use to access Kafka. We're only going to focus on a couple of them, but there have been a few that have built up over the years as Kafka's evolved and come with a brand new set. And then we're going to talk about compacted topics and using compacted topics, which we'll get to when we get there. It won't make any sense right now, but it will. Okay, so what is Kafka? So the main webpage, which is kafka.apache.org, says it's an open source distributed streaming platform, but that's probably. But it also mentions at various points that it's scalable, persistent, reliable, ordered, and real-time, and we're going to go through what each one of those really means. It's scalable to many messages a second, in 1,000 to million messages a second sort of range. I've only ever pushed it to the 100,000 messages a second range, and in production, I've only pushed it to the tens of thousands of messages a second range, but you know, it can do them. Persistent, because it is, as well as a messaging system, it is also a data storage system, which is something that's often overlooked, but is actually very powerful. It is reliable because you can, and has happened, boxes can just disappear from underneath it, and it just keeps ticking. Some functions stop working if you get too many failures, but generally it just keeps going. And I'm yet to have Kafka lose any of my data. Some of my code on either side has, but Kafka hasn't. It guarantees ordering for some messages, which is important. We use it. One of our biggest streams is click streams. So every click on the hotels.com website will generate a message which flows over Kafka. And the ordering is important because it means that when we look at a session, we can see what happened in the order on that session. So we can then later on use it to work out flows through the site and optimize for them. And it's real time. Real time's a funny word, but real time in this instance means that it is sub 10 millisecond get from one end to the other, pretty much all the time. Right, jargon. How slow am I talking? I'm doing okay. Right. So each one of these is going to be a slide, so be ready. There will be a test. Okay, so we've got, I've got a laser. Producers, consumers, which are fairly obvious. They're the things that generate the messages and the things that consume the messages. Brokers are the servers in the middle, orchestrate moving the messages from one side to the other. Clients are either the producers or the consumers, but we also talk about groups for clients. Topics, so Kafka has each has named topics. Each topic has a partition. Each message within a topic and a partition has an offset. It's all right, we'll get around to these. And consumers are grouped. And each message is actually a key and a value. These lovely images were just stolen from the Kafka documentation. There are some that I drew, and they're worse. Okay. Am I moving around too much for the camera? Yeah, thought so. That's good. Okay, so yeah, this is fairly basic. This diagram in the new version of the documentation is much more complex because they've feature bloated a little bit. But generally, things do one of two things. They either produce messages and send them into the cluster, or they consume messages and take them out. Sometimes one of these is actually one of these at the same time. But mostly, you end up with producers and consumers. A typical example from my world is a producer tends to be one of the edge apps that provides details of a hotel, and a consumer is what is a consumer? Well, we have various consumers, but some of the consumers may be trying to think of an example that I can actually share. So some of the consumers are, say, a system which generates an annoying pop-up that says 36 people have looked at this hotel in the last hour. Sorry. I may have had something to do with that, but only superficially. Yeah, just that bit. Okay, so producers generate messages. Messages are a key and a value, and consumers consume the messages. A message is, as I said, just a key and a value. There is a timestamp, which is optional, which you can use for tracking the message through the system. And you can also use it in place of an offset, which I'll explain later. But that's the data structure that is a message, and this is what gets written out to disk and what goes over the network. And it really is the most simple data structure imaginable. It's basically checked, has a version, and some flags, which say whether it's compressed or not. Hang on. Nope, that's it. Okay, so a topic. So a topic may be is a name. It's a single subject that you're interested in. So let's say our topic is orders on a website. Each topic is split into partitions, and you can choose to just have a single partition, but generally you would end up with several partitions, 12, 60 odd partitions. And so a message gets put onto a partition. So each one of these little boxes is a message. The order, which I mentioned earlier, is only guaranteed within a partition. So when a message arrives in partition 0 and then a subsequent message arrives, they have an order, and that order is immutable. Once a message is written into what's called a topic partition, which is one of these horizontal stripes, it's immutable. It stays there then forever until it gets old and deleted. And they're ordered. What decides which partition a message goes onto is either you decide when you send it the message, or it's decided from the key, which is the most likely use case. So the key is hashed and put onto there. So for the key, for us, we tend to use a customer ID for this. This means that all the orders for a particular customer are guaranteed to appear in order on this partition. So if we start reading this partition from there, we see the orders from that customer in order. Or the clicks from that customer in order. Sorry, did I cover everything? IDs are sequential, and a topic can have multiple subscribers. So although you can have multiple people writing into the topic, although the order is only guaranteed from a single producer, you can have many consumers reading off of that. And the way a consumer is they ask for a offset. So say you're a consumer, you go, okay, I want to start reading from offset 9. So you get message 9, then you get 10, 11, 12, and so on. But someone else can also be reading from this, and so they'll start reading from, say, 4, and they'll get 5, 6, 7, 8, 9, 10, 11. And they'll keep going. And the only thing that's recorded against a particular consumer is the consumer's ID, or the consumer group ID, more accurately, and its offset. And that's the only thing we need to remember. Kafka can remember that for you, or the consumer can remember it itself in some other system if it wants to. This means that, and because we store all of these on disk, it means the consumer can come back. So if consumer B leaves at offset 11 and we start writing message 700 or whatever, consumer B can later reconnect and restart, remember where it got to, and start processing from there going forward. We use this because we do a whole bunch of offline analytics as well. So we will have a system that wakes up, say, on an hourly schedule, remembers where it last got to, looks at where the current thing is, and just reads everything in between there, writes it out into S3 or into Hadoop HDFS, and then goes back to sleep and wakes up next hour and does the same thing. It means we don't need to have something running continuously, and it also means that if it fails halfway through that, it just restarts and tries again if there's a transient network failure or something. Typical retention periods for these things, I think the default out the box is 24 hours. We set it to 7 days. The main reason for 7 days is that if something goes wrong and it's a long weekend, no one actually has to worry about it until Tuesday because we haven't lost any data. Some processes may need to be rerun, but basically if you can't get hold of anyone, no one needs to be on call for the offline stuff because we've got 7 days worth of data stored on there. And disks are cheap-ish, particularly if you're not paying for them. Consumer threats. Yep, that's the only data persisted by a consumer group. Right, so then what is a consumer group? Now this is where it gets a bit clever. So this is used, I guess the heaviest use we have this for is some of the marketing analytics tracks sessions. So it looks at sessions and where people came from based on whether they came from SEM, SEO, how much we paid to get that customer onto the site. And that's a lot of traffic, and these things are doing a lot of work. So they can't hold the whole current model in memory. So what you end up with is a consumer group. So we write the software that consumes a stream based on a browser ID. And we just launch 12 of those. When you do that using the Kafka client, each one launches and connects to the Kafka cluster. Each consumer will actually connect to every broker, every server within the cluster. And it will be assigned some of the partitions from that thing. If you launch a second one, then Kafka will automatically rebalance the partitions between those consumers. So that means that each of the messages on these 4 partitions, only a quarter of the messages are actually going to each one of these, but every message goes to one of them. So every message is delivered, but only to one instance. And because we key each one of these on browser, each one sees every click from a particular browser in order. And that means that then they can window the thing by session and then pass session onto another queue in Kafka, which then goes further down. But that's a complete session windowing is a completely different talk. Cool. Sorry, did everyone get that? Because that's a tricky concept. At least it was for me. Okay, everyone here is smarter than me. Cool. Right, so that's it. We've covered... Sorry, Luke. We've covered what all the different bits of Kafka. So there are producers, there are consumers, there are brokers, there are topics, there are partitions, there are offsets within those topics and partitions. And that's Kafka. It's fairly simple to distribute. It relies on Zookeeper under the hood in order to coordinate all of this. It doesn't use Zookeeper very heavily. It used to use it much more heavily, but now it uses itself to store those offsets rather than Zookeeper, and just uses Zookeeper for coordination amongst the cluster. It also scales ridiculously linearly because each one of those topic partitions is just a file on disk, and it writes to the end of that file. Even on spinning disk, it's just writing to the end. That's actually the most efficient way of using a spinning disk. And the consumers are also reading from a point and then reading forward, which means that Kafka just scales. You can put it on a machine with 30 terabytes worth of disks, and it just handles it. You launch Kafka, the JVM by default just sets up with a gig of RAM for heap, and the rest of the RAM is all used by the operating system as disk cache. And yeah, it really does run very fast, even on EC2 instances. Last time I tried to benchmark one of our systems, I couldn't generate the messages fast enough and topped out at 500,000 a second, which was pretty good, but was a bit of a waste of time because I was only supposed to go to 10,000, but it just kept going faster. I just wanted the graph to go up. Okay, so there are several APIs to get to Kafka. There are more than is listed here, in fact. So the producer API, which we'll come to in a bit, and there'll be code samples for generating messages, is a Java API. Kafka itself was originally written in Scala inside LinkedIn. Since it's moved to Apache, a lot of the stuff has been ported, at least the client-facing APIs are now written in Java because Java integrates better with the other JVM languages. So the producer API, there are two old ones which are written in Scala, but the new one is now in Java. The same with the consumer API, which are, and these, as you can guess, are for generating messages and consuming. There is, since Kafka 0.9, there is now the Streams API, which is looks a bit like the streams in Java 8. It's a very fluent way of handling messages where you get a stream, you pass it through various functions, and then you pass it out to another stream. And you can join with various streams. It's a nice way of writing stream processing systems without having to launch inside another cluster, such as Spark. You can just write these streams things and then just run 12 of them, and it will distribute over 12 partitions quite nicely. The Connect API came out of Confluent, which is a company that was spun out of the original guys at LinkedIn in order to back, and are the main contributors and backers of Kafka. And the Connect API was written in order to allow you to source and sync data into external systems. So, and we'll come to that. It also has a binary network interface, which you can talk to directly. I wouldn't recommend it, because you have to talk to all the brokers and handle distributed network processing, which is hard, so use someone else's code. But there are clients written for other languages, but I haven't used them, so I'm not going to talk about those. I know nothing about them. Right, yep. And the wire protocol is just Apache Kafka /protocol, and you can read all about it. So how you use Kafka. Connecting to Kafka is really quite simple. All you have to do is say where Kafka is, give it a simple class which says how to serialize something down to a byte array. The serializer interface is very simple. It just give me your object from bytes, or take this object and give me bytes. You implement two functions, you're done. There is a string serializer, there is a byte buffer serializer, there's a byte array serializer, but neither of those two do very much besides wrapping things. But there are several, and the way we commonly use it is we just use Jackson and go from JSON back, or use Avro and do the same thing. Once you've defined your properties, and these are the minimum set required to make it work, there are other ones, such as the number of acknowledgements you need, whether it needs to be written to disk, how many brokers need to have written it to disk first, those sort of things, and lots of buffer sizes. There are pages of options, but those are the only three you need. You then just create a producer using those properties, And then you send a producer record, which is just the topic name that you're going to send it to, and 2 strings. You're done. Internally, it will buffer these up and send them out. There are various callbacks you can put on this to get notified when things have been sent, but that is pretty much it. You then have to close it. A lot of things in Kafka don't implement closable, so you have to close them, or you have to tell Spring to call the close method. But that's it for the producer. The consumer is very similar lot of code. There you go. It gets a bit exciting with the consumer because you've got this idea of committing. So if you remember from a few slides back, 10 minutes or so, we talked about offsets. So in each consumer group, which you also identify yourself as, you have an offset. And when you connect, if no offset exists, then by default, it will start giving you messages, the next message that arrives. You can also tell it to go back to the beginning of history if you want to, and that is important for some use cases. But you can tell it to automatically commit. This means that when you get records, every so often, it will just record where you got to. It will send back to Kafka, say, okay, mark here, this is where I've got to. And by default, I think the default is 5 seconds. Yes. So this means that every 5 seconds, it will just mark that you've got to here. So if your program crashes and starts again, you'll repeat some messages, and that's the thing about Kafka, is its normal guarantees are at least once. So you will get the message, but you might get it more than once. And that will be the case in this case. If it crashes, you will start again. You might get some messages repeated, but you won't lose out because you won't have committed anything you haven't already received. Of course, you may, because it's auto-committing, you may have received it here but not actually processed it. And that's why you can disable auto-commit, and on the consumer here, there is a commit message, and you can say commit these offsets for these partitions. The usage of it is fairly simple. So you call poll and give it a timeout in milliseconds. You get back consumer records. Consumer records is iterable, so you can do a for each loop over it. Each one is a record, and records contain a whole bunch of information, such as the topic, partition, offset, the key, and the value. You can then collect those and record you're guaranteed to get them in order, so you can record the latest offset and per partition that you have got, and then later commit that back to say, okay, I've processed this, it's reached the end of my pipeline, I don't want to see it again. Yep. Okay. And this is the Streams API, which is new, and I haven't used this yet. Other teams that I've got have started using this, and they like it a lot. But I haven't had the chance yet. It's a bit depressing. So this is the same thing, only they've decided to change the serializer class, and it's now called SERDES. So this is the string SERDE. The Bootstrap server is the same thing. It will go and talk to this one and discover the rest of the servers. You only need to talk to one of them to get it, although you can give it a list, so it will fall back. But with Kafka Stream, it's basically a case of you build it. So you give it a name, you do some things to that. So in this case, it's just taking the value and returning the length of the value as a string, and then writing it to another topic. Then you start this stream, and that's it. Your application is just going to run and call this method or this function for every value that comes in, which is pretty cool. And so, we're using it for various. I think mostly it's been used for just as sanity checks on some streams and for metrics logging. But I can see a case if we can persuade the data science team to write their stuff that fits in that box, we'll be good. Okay. And then connect. Yeah, connect. I don't like connect. So connect is it's designed to let you go from Kafka to something else, or from something else into Kafka. So you can use it to pull stuff from S3 or HDFS and push it into Kafka, or you can pull stuff from there and push it out to Elasticsearch or to Postgres or whatever. It is a server that which you run. You can load various connectors into it and configure them via a REST interface. So a REST interface, you configure which jobs are going to run within the workers, and it will scale out between all of these workers. And it stores all of its configuration in Kafka as well as its offsets and all the config. So that's quite cool. So it does all of its storage within Kafka and uses Kafka to generate its stuff. The connector API is better than it was. And basically, you just write async that handles stuff and occasionally call flush when you're ready to write what you've been given out to disk and then commit those offsets. And it does work very well. And the REST interface is ridiculously easy to use. It didn't quite meet the constraints that we were using, but for general use cases, it's good, although we didn't like the S3 endpoint because it was built on top of the HDFS one. But we're in the process of open sourcing the one we wrote. And that's it. So yeah, if you use one of those things, if you're unlucky enough to use that one, it can be pretty good. Cool. Right. Wow. Okay, got a few minutes. Right. So if you remember back to the topics, so a topic is made up of a sequence of a set of partitions. Those partitions don't necessarily have to live on the same disk or in the same broker, and they are also replicated. So each partition will actually be written onto as many brokers as you like, normally 3. Normally, the cleanup policy, which is a configuration you can specify for a topic, is delete. And what that means is that after it reaches a threshold either of time or size, and you can specify one or the other or both, it just deletes the oldest stuff. So, like I said, the normal retention period, the default retention period is 24 hours. That means that after 24 hours, whole files worth of logs, and it cycles the files every so often, get deleted. And you cannot go back that far. Why 7 days is good, because 4-day weekends are 4-day weekends. However, there is a new thing that was introduced in 0.8, which is this idea of compact topics, and they're fun. So compact topics basically give you a write log. So in a database, database will write out each of its transactions and then periodically clean them up so that it has the complete state in there, but anything that's old or been overwritten is removed. And log compaction does that as well. So it means that when you write a key into that particular topic, the last value you associated with that key will be kept. Anything before that last value is fair game for being cleaned. What this means is that you can have a key value store so that anything that comes along can read from the beginning of that topic and to the end. And when it's got to the end, if it's looking at if it's keeping the state of all of those keys, it has the latest version of the data. And what we've been using that for is as a distributed key value store. And it's also what Connect uses for its config management as well. So what Connect will do, and what we do, is set up this topic. Any changes to our model get written against a key. Everything in the distributed system that's interested in that particular data store subscribes to that topic, and what we maintain is an internal hash map which gets written. So anyway, an example, because I've probably skipped ahead a couple of slides with that talk. So if we've got the log here, so we have our offset from the epoch out. So we've written key 1 with value 1, key 2 with value 2, and then written key 1 again with value 3, and key 1 again with value 4. When Kafka comes to clean this log up, it will see, okay, so this is the most recent key 1, so I'm going to keep this one. These two are gone, so we're just going to maintain the last one, and so on. And so you end up with just the keys and their last values. So if I came with, say, a hash map and read and wrote each one of these into the hash map, and I did the same here, I would end up with the same hash map at the end of it. It's not always that easy, because it is required that it leaves the head of the log alone, because if this is fairly high velocity, if we've got lots of messages coming in at a time, it may be that some of our consumers are a second or so behind, say. Garbage collection happens to everybody in the Java world. Kafka will typically leave the head alone, and you can specify how much this is, and then it will start cleaning from the way back. The offsets of any messages that it comes across won't be changed. Each message itself, with its offset, its key, and its value, is immutable. So we now have non-linear. Well, they're still linear, but they're not incrementing one at a time. So we'll end up with gaps. It does mean that if you come in and say, okay, the last offset I got to was 51, the next message it will give you is 53. It won't give you 51 or 52 because they no longer exist. So as far as this is concerned, everything from 41 to 52 gives you 53 next, and so on. Which means that when if you've got your state from there and you read through, you're not going to miss out on anything, because anything's going to be overwritten by the time you catch up. So apart from, you're in a funny state while you're catching up, but you get there eventually. Cool, right. So using those, so this is what I was explaining before. So what we wrote was an interface that implemented map, and it delegated everything through to these two functions. Put and get, so put all just calls put lot, and so on. So we put a message, we translate it to bytes, we put it on our topic. We also listen to that topic, we translate things back to whatever the key value is, and we put it in our map. And that was it. It gets a little bit, there are some tracking bits around here, so that we actually block here when we put the message on the Kafka topic until we see it come out here. But generally, this works, and we've launched this and run it around the place. And so there is a Kafka compact log class inside Kafka Connect, which allows you to implement a lot of this. What we found was we ended up with a problem where this data structure that we were putting in was quite large, and each component in our system only wanted to update a small part of it, but it was doing a put with the whole value, and so things were overwriting each other. So now this is read-only, and we have a central thing, so we have another topic which is updates, which goes to a central thing which orders them, so they only happen one at a time. But yeah, and I will try and get some code out to do this, but we have an open source approval process, and it takes a little while to go through. Okay. That is it. Thank you very much.